The ionization constants for acids and bases, Ka is the acid ionization constant. It tells you how much the acid ionizes in water, and it gives you a measure of the acid strength. Strong acids have a Ka greater than 1. Weak acids have a Ka less than 1. Kb, on the other hand, is how much a base ionizes in water, or a measure of the base strength. Again, strong bases have Ka greater than 1. Weak bases have Ka less than 1. Sorry, Kb. So, in order to figure out what the expressions for Ka and Kb look like, we have to consider the chemical equation for an acid or a base ionizing in water, respectively. For an acid ionizing in water, in general, the chemical formula of the acid will be Ha. We're reacting it with liquid water here. So H2O liquid. We'll end up with a hydronium ion and an A- ion, the conjugate base. Ka is just the equilibrium constant, concentrations of products over concentrations of reactants. So it's going to be the concentration of hydronium times the concentration of the conjugate base divided by the concentration of Ha, the unionized acid. And we don't include water in the equilibrium expression because it is liquid. So the larger Ka, the greater the ionization. You may see acetic acid written as HC2H3O2, or you may see it written as CH3COOH. This is the way an organic chemist would write it. When acetic acid ionizes in water, we get hydronium and acetate, CH3COO minus, both of these in the aqueous phase. So, Ka for acetic acid is equal to the concentration of hydronium times the concentration of acetate over the concentration of unionized acetic acid, CH3COOH. And the value for that is 1.8 times 10 to the negative fifth. In other words, acetic acid is a weak acid. So we're going to use this information to do this exercise. What's the pH of 1.0 molar acetic acid? So we're going to make an ice table, solve it for X, and that'll be the concentration of hydronium. And so the pH will just equal the negative log of X. The initial concentration, 1.0 molar for the acid, 0 and 0 for the H plus and the CH3COO minus. The acid's going to decrease by X, and the H3O plus and the acetate will both increase by X, since we're starting out with no products in all reactants. At equilibrium, we'll have 1 minus X, X, and X. Let me remind you that the value of the equilibrium constant is 1.8 times 10 to the negative fifth, and that is equal to the equilibrium concentration of hydronium times the equilibrium concentration of acetate over the equilibrium concentration of unionized acid, CH3COOH. So, we take the equilibrium values from the ICE table, and we end up with x times x over 1 minus x. So 1.8 times 10 to the negative fifth equals x squared over 1 minus x. So we could make that into a quadratic, or we could do a shortcut, and we could recognize that since the KEQ is much less than the initial concentration, right? So our initial concentration is 1.0 molar, and that's much less, or that's much greater than our KEQ value. That means that x will be much, much less than 1. And therefore, 1 minus x, that is 1 minus a very small number, will approximately equal 1. And so this means we can make the approximation that x squared over 1 minus x is approximately equal to x squared over 1. So now we say x squared equals 1.8 times 10 to the negative fifth, and x equals the square root of 1.8 times 10 to the negative fifth, which is equal to 4.24 times 10 to the negative 3. And that's equal to the hydronium ion concentration. pH is equal to the negative log of the hydronium ion concentration, so that's the negative log of 4.24 times 10 to the negative third, which gives us 2.37. 2 sig figs. Right, and this makes sense because this is a weak acid. For a strong acid, the pH of a 1.0 molar solution is 0. Here our pH is significantly higher.